Hi everyone. In today's video, we are going to explore Silvaco TCAD, a powerful tool used in VLSI and semiconductor device design. We will also look at DACA build, the simulation control environment that helps us set up, run, and analyze TCAD simulations. This video will give you a quick overview, while the detailed installation process of this Silvaco TCAD tools like DACA build and Tony plot and dev edit and etc tools is explained in the another video, which is linked in the description below. So let's dive into the topic. At first, we'll look at the code which is present here. At first, we will begin with the mesh. The mesh divides the device into small grids where calculations happen. Finer mesh is used near the gate oxide and junctions because that's where the critical effects like charge distribution and electric fields must be captured accurately. As we all know that the MOSFET contains, the 2D MOSFET contains two coordinates, x coordinate and y coordinates. So we have to define x mesh and the y mesh at first. X mesh defines the mesh in the x direction, and the y mesh defines the mesh in the y direction. LOC means the location where the mesh should be located, and SPAC means the spacing between the meshes. In this way, we have to define meshes. After that, we have to define the regions and assign materials also. As we can see that in the code, the region 1 is air, and the region 2 is SiO2, and the for the gate oxide, regions 3, 4, 5 for the source, channel and drain, and region 6 is for the silicon substrate. Together these form the MOSFET structure. So we have to define these regions and their materials present in it and their coordinates like x minimum and y minimum, and x minimum coordinate and x maximum coordinate, and y minimum coordinate and y max coordinate for the clear region presentation. After that, we have to define the electrodes. The gate is placed above the oxide, the source is on the left side, and the drain is on the right side. These are the terminals where the voltages are applied. Like we all know that MOSFET contains three electrodes like gate, source and drain, and as well as mentioned above, we have to mention their coordinates also. And then now we add doping. The substrate is p-type, the channel is also lightly p-type, and the source and drain are heavily doped n-type. This creates an n-channel MOSFET structure. As we can see that the concentration of p-type is 10 power 18 per centimeter cube, and the concentration of region 3, which is n-type, is 10 power 20 per centimeter cube. In this way, we have to mention the concentration and the type of region also. We then define the interface charge at the oxide silicon boundary to make the device realistic. Contacts are also added with the gate having a defined work function, while the source and drain are ohmic. In this way, we should add the contact names like gate, source and drain, and we also define the work function here as I highlighted that one. To capture real device behavior, we add models for mobility, recombination, band gap narrowing, and field effects. The Newton method is used to solve the equations which will be present in the MOSFET structure preparation. The ConMop is the very famous model which is very useful in VLSI and AVLSI. So after that, we have to use the Newton trap method for solving the equations. And then in outputs, we choose what to observe like band diagrams, electric fields, currents and mobility. The simulation then applies 0 volts at the drain at first, as we have to design this for five cases with different V drain values for the comparison of conduction band energy. So the code works for only one V drain value at once. So we have to comment other V drain values like this. For each case, we should uncomment this line and comment another V drain value. And a gate voltage of 0.75 volts should be defined and saves the results in Tony plot, and the file will be named as cl test6.str. So now we'll check about the results that will be presented here. I am opening the Tony plot by clicking on this icon. Yeah, in this way the 20 port will be open, and we have to open the files. At first, I'm opening the structure of MOSFET by clicking on this file. As you can see that this is the structure of MOSFET that was designed by ourselves. After that, we can also see the graphs which are designed by us. This is the graph between drain current and the gate voltage, as you can see here. So I am deleting this one. Next, we can use cut line for seeing the horizontal section of the MOSFET by dragging this from one end to another end. This cut line can be made by selecting on tools and then selecting the horizontal cut line and then OK, and we have to drag that line from one end to another end. So we can see the absolute net doping of source, drain and gate. From this graph, we can see the conduction band energy graph by right clicking on the graph and display, and we have to select the conduction band energy and deselect the absolute net doping and apply. This is the conduction band energy graph. So we can also see the vertical section of this MOSFET. So same, by selecting the tools, cut line and selecting the vertical line, and by dragging this from middle to other end. This is the vertical section. So now I will try to compare these both graphs. So I will delete this one. To compare any two graphs, we have to select all the graphs that are present in the screen. You can see this option has select all plots, so I am clicking that one. This will select all the plots that are present on the screen, and then we have to go to edit and make overlay. This makes the comparison of two graphs. This is the comparison of two graphs. So after the comparison, I am deleting these all graphs, and I will open another file. Files may take some time, but they will open confirmly. After this one, this is the MOSFET with larger VDS and smaller VDS. So for this also, we will see the horizontal section. This will be the horizontal section, and I'm deleting this MOSFET also. From this, I will display the conduction band energy graph by right clicking on it, display and conduction band energy, deselecting this one and apply. This is the conduction band energy of MOSFET having larger VDS and smaller VGS. So now I will compare these graphs, these two graphs, with by selecting all plots and edit and make overlay. This is the comparison of these two graphs. Okay, as you can see this is the comparison graphs. So I made some samples and make the comparison between these samples. The picture will be I will show here. This is the comparison, and this shows the conduction band energy across MOSFETs. As gate voltage increases, the band bends towards near the channel. This indicates electrons are attracted, forming a conductive path. It also demonstrates how the gate controls channel formation and current flow. In this way, we can see that I have also made graphs between increasing VGS also, and in this graph the conduction band under different gate voltages, it will be displayed here. Band is bending smaller compared to the first case. As we can see, the band is bending very smaller when compared to the increasing VDS case. It suggests the weaker gate control or thicker oxide, so inversion happens later in this manner. In this case, it also highlights the threshold voltage behavior of MOSFET. So now, by combining all these three graphs, I made another final result graph which is stored in this file. This demonstrates as conduction band for multiple increasing gate voltages. As you can see here, this red graph is for larger VDS, and this green graph is for larger VDS and smaller VGS, and this blue for larger VGS and larger VDS. This also, in this graph you can see that band bends more strongly at the channel, showing stronger inversion. Clear transition from weak inversion to strong inversion. This graph also explains how MOSFET switches from off state to on state. In this way, we can make all MOSFETs and compare all the graphs. So we can also see the doping concentrations of the MOSFET. I will display that one also. I will delete all this. This is the MOSFET, and we can see the doping concentrations also by right clicking on it and display. We have to select contours. This option is for contours, and apply. These are the different doping concentrations of the MOSFET. We can measure those concentrations from this column as suggested below. In this way, we can make any other MOSFETs like N MOSFET, P MOSFET, and any other devices by giving the suitable code for them. This code will be posted in the drive link, so you can take this code also. Thank you.